Dear all, and welcome to my presentation for our paper today with the title Explainability of the Implications of Supervised and Unsupervised Face Image Quality Estimations through Activation Map Variation Analysis in Face Recognition Models. My name is Biying from Fraunhofer Institute from Darmstadt. Today, face recognition systems are becoming more widely used in our daily life, be it for security-relevant areas such as the border control or for unlocking your personal devices like smartphones. This spread is strongly related to the performance improvements due to the advances made in deep learning-based methods for face recognition. However, the high performance of face recognition solution is also related to the quality of face samples used. Low utility face samples would largely affect the performance of the face recognition algorithms. So face image quality is directly correlated with face utility to determine if a face image contains the discriminative features for the task of face recognition. Face image quality is unlike the general image quality, which could be explained by the perceived image quality. Face quality is a score just used for an algorithm. Here, we illustrate a simple pipeline describing the process of assigning a quality score to an input face image. And first, the face image will be pre-processed by using a face detector and alignment, and to output a standardized face image, which is further processed by the face image quality assessment network to calculate a final quality score. This quality score is used to determine if the input face image is of high or low quality. Here, the face image quality assessment measure is specially designed to relate a face image's quality to face utility. And only high quality images can be used to enhance the performance of a face recognition system. The categories of face image quality assessment methods are large. As simplified by this tree diagram, we can see that these methods can be mainly divided into supervised, unsupervised, or feature-based methods. Supervised methods mainly learn with pseudo-quality labels, such as STD, FIQA, or face QNet. They require data with labeled quality images. But the unsupervised methods like SER, FIQ, it relates the face quality directly to the robustness of the face embeddings. The advantage of this unsupervised method is that it does not require ground truth labels with these pseudo quality labels. So it can be more generalized and applied to different images. And the feature-based methods are mainly derived from the handcrafted features defined by the ISO standards, such as blur, illumination symmetry, inter-eye distance, or exposures. These single quality factors are mainly derived from the spatial domain of the input image. And due to the recent advances and interest in this research field, the diversity of these methods is immense, but less work focuses on showing the explainability directly. Therefore, the main scope in our work aims to propose a novel set of explainability tools to derive reasoning for different FIQA decisions and their face recognition performance implications. To enable our tools to be deployed to both supervised and unsupervised FIQA approaches, we do not look directly into the responses of the FIQA approach itself, but rather at the face recognition model behavior when processing images with various FIQ decisions. Our newly proposed tools aims at answering the following 3 research questions. The first question is, what makes the face images of high quality in comparison to low in the view of different FIQAs based on the face recognition model behavior? The second question is, what makes the decision of high or low quality different between different FIQAs based on the face recognition model behavior? And the third question is, how do the activation mappings caused by face images in the face recognition model deviate from what is expected from high quality images, and how does that reflect in their quality scores? But before we come to answer the posed questions, I'd like to shortly introduce our proposed toolset first. In the first step, we select one FIQA method to determine the quality scores of a face database. Ranked with these quality scores, we then separate the images into high and low quality sets. In the second step, the activation mapping is used to derive the network's activation of a face recognition solution for both groups of high and low quality images. In the third step, our main toolset are based on the statistics derived from these activation maps and the individual group settings. For more details, we refer to our paper. In our toolbox, we first analyze the mean average mappings as shown in the first row, but we also look at the variations of the mean average mapping as here illustrated on the second row. But what is more interesting is the difference of the variations as indicated here in the third row, because this provides a useful tool to analyze the difference in face recognition model responses to sets of facial images belongs to different sets. Here, for example, we look at the difference between high and low quality images determined by the same FIQA approach. But this can be used for different setups and groupings. Now to answer the first question, what makes the face image of high quality different to low quality images? In the view of different FIQAs, we consider the mean activation mapping of the individual FIQAs with respect to the high quality and low quality image sets. As we can see from the red box, we observe that no major difference is observed for mean activation mapping for high quality and low quality images. This could indicate that the effect of quality differences as per different FIQAs on the face recognition model is of the same nature. This is also confirmed when we look at the distributions of the mean average mappings for high in red and low quality images in blue. These distributions are largely overlap with each other. However, if we go to higher derivatives by looking at the variation maps shown in the green box, here we spot that variability in activation mappings is stronger for low quality images. Here, compared to here. Especially we see that for low quality images, strong variations can be seen on the borders of the left and right corner. These are the areas outside of the center face. The difference map further indicates the focus of low quality images on areas outside of the face center, while the high quality images consistently have low focus on these regions. So simply put, the low quality images do attract the attention of face recognition models, especially in areas outside the center face area, but however in different locations and are less consistently. This is also confirmed by the distributions of the variations. We see that strong variations are observed for low quality images, as marked in blue, compared to high quality images in red. So the question, what makes the decision of high or low quality different between different FIQAs based on the face recognition model behavior? We want to observe this across different FIQA methods. Therefore, we look at decisions for high and low quality across different FIQA methods. Like we compare BRISC to face QNet, BRISC to MACFace, and face QNet to MACFace, and MACFace to SEI FIQA. As marked in the green box, we see samples selected to be low by the supervised methods like face QNet or BRISC tend to have higher activation variations on the left and right edges of the face images compared to MACFace. It's shown here in the second and third row. This consistent activation variation on areas outside of the face center might be a rationalization of the lower performance of these methods, like face QNet and BRISC, towards MACFace on the other side. So the last questions deals how do the activation mappings caused by face images in the face recognition model deviate from what is expected from high quality images, and how does that reflect in their quality score? In this figure, we show sample images with the deviation from the mean activation mapping from high quality images. Left are the samples of the high quality images, and right are the samples of low quality images. These highlighted areas in the images are supposed to show areas which could cause the degradations in quality as they deviate from the mean template of high qualities. It can be generally concluded that for all FIQA methods, larger deviations are observed for low quality images in comparison to high quality images. In many cases, it is related to reasons like less optimal poses, face occlusions, or overall low image sharpness. To conclude, we can say that low quality images tend to have a face recognition model activation map that strongly differs than that of what is expected from a high quality image, especially more apparent in the areas outside of the central face region. Thanks for listening to our presentation, and we are now available for questions.